Look up at a storm, and the roiling clouds look like pure, unpredictable chaos. Lightning branches wherever it wants. Mountains jut out in jagged spikes. Our basic human intuition tells us that the natural world is entirely random. To make sense of our surroundings, we rely on classical geometry. We measure reality using perfect spheres, clean triangles, and smooth curves. But real nature rarely cooperates. Try fitting a clean triangle over these rocky mountain peaks. It fails completely. The harsh, irregular spikes refuse to conform to a smooth outline. For centuries, mathematicians treated this roughness as an annoying imperfection, a series of flaws that lived outside elegant mathematics. Dismissing those irregularities actually blinded scientists to the deep physical rules sitting right in front of them. Take a seemingly obvious scientific principle. A physical object has a stable, finite size. You can measure it, and you will get a concrete number. This animated diagram illustrates a famous geographical experiment measuring a coastline. We start by laying a rigid 100-kilometer ruler around the map of Britain to establish a baseline length. Now watch the total length counter when the ruler shrinks down to 50 kilometers, and then down to 1 kilometer. A smaller scale dips into previously unmeasured bays, inlets, and tiny cracks. The closer you look, the longer the coastline gets. If you take this to its logical conclusion and use an infinitely small ruler to measure every single grain of sand, the measured length of the coastline approaches infinity. In the 1960s, a mathematician named Benoit Mandelbrot looked at this anomaly and asked a dangerous question. What is infinite irregularity is actually the primary mathematical rule organizing the natural world. A physical coastline resisting a fixed measurement proved something unsettling. When applied to real-world biology and geology, classical geometry was broken. Mandelbrot's insight relied on self-similarity. Look at how a large tree trunk splits into medium branches and then splits into smaller and smaller branches. The exact same angle and proportion repeats itself at every single scale of the structure. To test if this repeating behavior could be mapped computationally, Mandelbrot used a surprisingly simple iterative equation. You take a number, square it, add another number, and feed the result back into the start, looping endlessly. When computers plotted millions of these calculations, the flat plane ruptures into shapes math had never seen before. Swirling boundaries, infinite spirals, and massive explosions of repeating geometry. Zooming deeper into the boundary didn't smooth out the image. Magnifying it 1,000,000 times or 1,000,000,000 times continuously generated completely new, intricate structures. Infinite complexity and structures so intricate they appeared almost alive were emerging entirely from one tiny repeating rule. Our brains are wired for integer-based dimensions. A simple line is one-dimensional. A flat square is two-dimensional. A solid cube is three-dimensional. These infinitely rough, self-repeating shapes shatter that whole number system. They force mathematics into a state in between. This introduces fractional dimensions. If you take a one-dimensional line and keep folding and crumpling it until it's so jagged it partially fills a surface, it exists somewhere between a line and a square. Britain's coastline calculates out to roughly 1.26 dimensions. That decimal specifies the exact rate at which an object's complexity scales up as you zoom in. Having 1.26 dimensions sounds like an absurd concept at first, yet it is the required mathematical language for accurately quantifying the real physical world. Once researchers knew how to measure this repeating architecture, they found it everywhere in biology. Human lungs and blood vessels use fractal branching to pack enormous amounts of surface area into extremely tight spaces, maximizing gas exchange. Look at massive energy discharges in the atmosphere. Lightning fires through the sky using those identical recursive pathways. Computer scientists generated hyper-realistic digital forests, mountains, and smoke simply by ditching clean geometry and feeding fractal algorithms into their CGI engines. The math maps onto time-based chaotic systems too. Economists analyzing financial markets discovered that short-term price fluctuations mirror the exact same volatile structures as long-term market crashes. Scale up to the extreme macro, and the deep space distribution of dark matter and galaxies cluster together in exactly the same self-similar patterns. By proving that what we perceive as total chaos is actually highly complex structural scaling, fractal mathematics bridged the gap between pure order and apparent randomness. The most unsettling realization occurs when researchers zoom endlessly into the Mandelbrot set. Waiting deep inside the repeating spirals are miniature, perfect copies of the entire universe itself. When you push the limits of human observation into mathematical infinity, you do not find emptiness. You find endless, hidden structure.